Welcome, everybody. It's my pleasure today to introduce Ling Zhou, and she'll be telling us about persistent homotopy groups of metric spaces.
Thanks for the Thanks for the introduction, and thanks everyone for joining this talk. I'm a PhD student from the Ohio State University. This project is done with my advisor, Facundo Memoli. Let's get started. So I want to start with a motivation for our project. So this picture came from a paper titled by Quantitative Homotopy Theory written by Gromov. In this paper, he mentioned a cute little story when he went to a lecture and he asked two topologists the same question, whether the universe is simply connected or not. It turns out that he obtained different reactions. And this makes him to wonder, maybe there are better questions to ask. How about asking how simply connected a space is instead of asking whether simply connected the space is? For example, consider this huge sphere with a very tiny handle. We know for sure it's not simply connected, but just looking at the space, it somehow makes sense to say the space is almost simply connected. And we believe our study of persistent fundamental group will give us somehow a notion to quantify the simply connectedness of spaces. In this talk, I will first give a quick overview of some previous work that blend homotopic groups and persistence implicitly or explicitly, and then I will talk about the details of our project. So let's move on to the first part. In the study of size homotopic group, Frosini and Mulazzani, they consider the sub-level filtration of a manifold together with a function on the manifold. Say it's a function from M to Rk. And by sub-level set filtration, I mean you can think of filtration where the functor f send each S to be the topological space given by this set. Or this figure will make it more clear. You can think of a manifold together with the height function. And one question the authors consider is, if you have two homomorphic manifolds, how do you quantify the difference between them? In addition, they introduced this notion of natural size distance between such homomorphic manifolds. And then they use persistent fundamental groups to estimate the notion of natural size distance. In particular, they consider the image of those induced map on the fundamental groups of the filtration. And they have a theorem to obtain lower bounds for the natural size distance from this collection of from this the notion of persistent fundamental group. That this work was done in 1999. A more recent work by Letscher in 2012, Letscher studied a notion, an invariant that comes from persistent fundamental groups to study the knouting behavior. In particular, he thinks of a filtration that's given by subcomplexes of S3, and then study the persistent fundamental group of this collection of complement spaces, and use he defines an invariant from this persistent fundamental group to detect whether the knot at step S is unknotted at a later step T. And there are also many works that study the properties or using different views to study persistent homotopic groups. For example, Blumberg and Lesnick, they formulate certain persistent whitehead conjectures. And Bantan et al., they study the persistent version of the Kempa theorem, excision theorem, and Huey's theorem. Jardine, he used a poset idea, the poset theoretical idea to study Vietoris-Rips complexes. And in addition, he also considered persistent fundamental group point in one of his lecture notes. So these, to my understanding, are some of the references that use the more like standard notion of homotopic groups and combine it with persistence. But in the literature, there are also studies that blend idea of homotopic groups and persistence from a different viewpoint. Those are called discrete homotopy theory. So this is quickly recalling how we would define the standard fundamental group. And the ingredients we need is the notion of loop, the continuous loops, and the notion of homotopy between loops. In the study of discrete homotopy theory, you will want to discretize everything. For example, instead of thinking of continuous loops, you think of a notion of discrete loops. And the way you discretize things will be scale dependent. That's how the persistence comes in. So more formally, take a parameter t, define the t loop to be the t-Lipschitz map from this finite set to our metric space X. So a T loop will be a collection of points, a finite collection of points in the metric space that start at x0, ends at x0, where each adjacent to has distance less than t. It's yeah, I think it's not difficult to imagine how this happens. And then we will need a notion of the discretized homotopy. So say for T homotopy. There can be many different ways to construct the notion of T homotopy. For example, Barcelo et al., they introduced the T homotopy between T loops using the following notion. You consider a T-Lipschitz map from this product of n elements, product of m elements equipped with the L1 metric for the product. Consider the map F from this to the metric space X. Or you can think that the map is of the following form. You can represent it with a matrix. By requiring the map to be T-Lipschitz under the L1 metric on the product, what you mean is that you require all of the horizontal, vertical, diagonally adjacent points to have distance less than t. So this is what happens when you equip this with L1 metric. And you can replace L1 with other metrics. For example, Plaut et al., in their setting, you can think that they are studying the discrete fundamental group by replacing L1 with L infinity metric. So you only require the horizontal and vertical points to have distance less than t, but not requiring anything on the diagonal. However, this is not how Plaut originally defined the discrete fundamental group. We figure out the relation between Plaut and Wilkins' study in our project. And let me right now introduce to you how Plaut originally defined their notion of discrete fundamental group. And the way they think of it is to introduce the notion of basic move on the T loops. It means that the addition or removal of a point, which is not the endpoint, such that the resulting loop is still a T loop, and define the T homotopy between two T loops to be that one T loop can be obtained from the other through finitely many basic moves. And with this notion of T loop, you construct the discrete fundamental group as scale T to be the collection of T loops quotient by the T homotopy relation. And let me emphasize that the notion I'm introducing on this screen was first considered by Berezovsky and Plaut in, I remember it's 2001. They were studying this notion in a more general setting, not necessarily just for metric spaces. And later on, in Wilkins' thesis in 2011, he continued this path of study and works on mainly metric spaces. So here I'm recalling how Plaut originally construct discrete fundamental group, and let me emphasize that you can relate these two groups of work by thinking that replacing the metric we equipped on this product. And then a more recent work by Letscher, the paper first appeared on ICAP in 2017. It was recently published last year, and Letscher is using the notion of check closure spaces to discretize or coarsen the continuity condition in the definition of standard homotopic groups. So it's, to my understanding, using a different language to study discrete homotopy theory. And so far, that's my review of all of the previous work. And for sure, I'm missing some. If you know there are interesting works that I should be looking at, please let me know. And the talk will, at this point, focus on the notion introduced by Plaut et al. And we will use this definition and the notation whenever we say discrete fundamental group, we mean this notation and definition. So in our project, we lift the discrete fundamental group into the persistent one by defining this functor, denoted as p-pi1. This functor sends each parameter to the discrete fundamental group at scale t. Send a pair of parameters to the induced map on the discrete fundamental groups. Let's consider the following examples. Take S1 to be the unit geodesic circle. Wilkins in his thesis studied the discrete fundamental group for S1 at all scales. Following from his study, we can obtain that p-pi1 of S1 is equal to z within the interval 0 to 2 pi over 3 and 0 otherwise. So the maps in the notion p-pi1 of S1 will be identity within this interval, identity on z within this interval, and it will be 0 maps everywhere else. The second example is when we consider a finite tree metric space. And in our project, we prove that T will have a trivial persistent fundamental group. So you can already imagine there are so many different ways to define persistent fundamental group. What are the relations between them? So let me mention some of them here. Take a scale parameter T. We denote the Vietoris-Rips at T to be VR less than T of X. So I'm using the open one, the open version here. And then I should use a full stop. That's a different story here. Okay, so starting from this sentence, I'm considering a notion of thickening of metric spaces. Let me explain that. So denote xt to be the open neighborhood of this image in the L infinity of X. So here you think of X embedded into L infinity of X through this map. So it maps every point in X to the distance function. And this is called the Kratowski embedding. And then you consider the thickening of X, the image of X in the L infinity of X. With these two notions, we can construct another two persistent fundamental groups, the Vietoris-Rips one and the Kratowski one. It's proved by Lim et al. In 2020 that there's the Vietoris-Rips one and the Kratowski one at the filtration level, they are homotopic to each other up to a scale 2. Then when we apply the persistent fundamental group, we would obtain the isomorphic between the persistent fundamental group, the VR version and the K version up to a scale 2. We can also relate the persistent fundamental group that arises from discrete fundamental group p pi 1 with p pi 1 of the Vietoris-Rips by using a standard fact where you see that the fundamental group of a simplicial complex is the same as the edge path group of the simplicial complex. For the sake of time, I will not mention too many details here, but for those who are interested, feel free to ask me. In summary, we have this natural isomorphic between these three notions of persistent fundamental groups. The next thing we study is whether the notion of persistent fundamental group is stable. We of course want the stability because we are thinking persistent fundamental group as invariants for the space. So it makes sense to require the invariant to be nice in the sense that when the spaces are closed, the invariants should also be closed. That's what the stability studies. Here I'm denoting p pi n to be the nth persistent homotopic group of Vietoris-Rips of a metric space X. Then we prove that given two metric spaces, the interleaving between their p pi n is less than or equal to twice of the Gromov-Hausdorff distance between the two metric space. So it is stable in this sense. In particular, for n equal to 1, we realize that the interleaving between pH1 is less than or equal to interleaving between p pi 1, less than or equal to twice of the Gromov-Hausdorff distance. So looking at this inequality, we can conclude that the p pi 1 would be a stronger invariant than pH1 in terms of estimating the Gromov-Hausdorff distance, because it lies between those two values. And we are about to see an example where we do see that p pi 1 performs strictly better than pH1. Consider the torus and this wedge sum of spheres. In addition, we think of the torus as this product of S1 with itself, equipped it with the L infinity product. And for the wedge sum space, we equipped it with the gluing metric. Then following from a result by Adamaszek and Adams, where they computed the homotopy types of Vietoris-Rips of S1 in both the open version and closed version, they have a complete characterization. And this space involves S2, so we also want to know the Vietoris-Rips of S2. However, it's still an ongoing question. We know partially what the Vietoris-Rips looks like for S1. For S2. For S1, we already know everything. For S2, we partially know it from Ling et al.'s work. So when we restrict ourselves to this interval 0 to 2 times zeta, using this the works from these two papers, we can compute PHN restricted on this interval for both spaces and see that PHN for them are isomorphic for any dimension n. However, their p pi 1 are not isomorphic. In addition, the difference between their p pi 1 would allow us to get a lower bound for the interleaving distance, which is at least the value zeta. As for the PHN, even though we don't know the PHN everywhere, but we can estimate an upper bound for the interleaving between PHN, which is about pi over 2 minus zeta. So comparing these values, you can see that p pi 1 would perform strictly better than PHN in terms of bounding the Vietoris-Rips complex. Sorry, what did I say? In terms of estimating the Gromov-Hausdorff distance in this example. So it's an example to justify our argument that p pi 1 is a stronger invariant. So that's the definition and some property of the persistent fundamental group. In the next part, I want to introduce dendrogram structure and a metric on the standard fundamental group that arises from p-pi1. I'm not sure everyone is familiar with this notion, so I'm going to start by introducing what I mean by a dendrogram. Given a set A, a dendrogram is the set paired with a map. Theta A is a map from the scale parameters to the set of partitions on A. For example, think of this 4-point set A. This is an example of dendrogram on this set. And how you think of it is when you slice the dendrogram, say at A, the little a, you obtain a partition of the set capital A by the singleton sets. If you partition the if you slice the dendrogram at C, you would obtain two clusters, the first cluster and the second cluster. The functions theta A will need to satisfy certain conditions. For example, eventually every branch will merge together into one. And Carlson and Mamoli, they proved in 2010 that there is a one-to-one correspondence between dendrograms over a set with ultrametrics on the same set. Here are some applications of the idea of dendrograms. You can see is used in the hierarchical clustering. Consider a metric space X, consider a scale T. You can define an equivalence relation between X and T that depends, between X and X prime that depends on the scale T in the following sense. Define this notion to be that X and X prime equivalent if there exists a sequence from X to X prime where each adjacent 2 points have distance less than T. So it gives you a way to gradually cluster the points in your metric space, and you will form a shape of dendrogram by doing this process. You denote pi0 T to be X quotient by this equivalence relation. I intentionally wrote it in this way so that you may compare it with pi1 T, the discrete fundamental group where you have the collection of T loops quotient by the T homotopy relation. So it's a similar construction here. And you can define an ultrametric on X by capturing the first time for 2 points to be clustered together. Here's an example of the dendrograms. And in particular, this example tells us that there are spaces which have the same zeroth dimensional barcode, but they have different dendrograms induced on the pi0. So the dendrogram on pi0 is a stronger invariant than the zeroth dimensions barcode itself. Here are 2 4-point spaces. And their zeroth barcode are given by these 4 intervals, but their dendrograms on pi0 are different. In fact, because the spaces are already ultrametric, the dendrograms on their pi0 will be the space itself. So you can already see the difference from this figure. And in our study, we were wondering, from what's happening with pi0, can we get similar structures in pi1? Do we have a notion of dendrograms in pi1? The answer is yes, when our space have some mild assumptions, satisfy some mild assumptions. And let me introduce that. So first of all, in Wilkins' study, he considered in the case when X is a compact geodesic space, and he introduced the following map. Take a parameter T, define phi of T to be a map that sends a continuous map to a continuous loop to a discrete loop that satisfies certain conditions. And he in particular showed that given that the space is geodesic, this homomorphism phi of t is surjective. So in that sense, you can think of pi1 of t as pi1 of x quotient by kernel of phi t. And therefore, pi1 of t can be viewed as a partition of the standard pi1. And this supports the idea for us to develop the dendrogram structure on pi1. In our project, we consider, again, the space is compact geodesic, but in addition, we require it to be semi-locally simply connected. Then we prove that when t is small, phi of t is indeed an isomorphic. It's not just surjective, it's also injective. And following from this, we realize that there is a dendrogram over the standard fundamental group that's associated to p pi1. So what we obtain here is that if you slice the dendrogram at scale t, you will obtain the discrete fundamental group at scale t, viewed as a partition of pi1. And let's continue to look at some examples. When X is a simply connected space, in that sense, pi1 is 0. And then following from this lemma, we already know p pi1 can only be trivial because pi1t is, because there is a surjective map from pi1 to pi1t. And now we can consider the following induced ultrametric on pi1 in a way very similar to what happened in dimension 0 when we considered a dendrogram on pi0. Here for pi1, we are tracking the first time when the discretization of two loops are t homotopic to each other. So phi t is the discretization map. And then for this induced ultrametric on pi1, we study its stability when we obtain the following. The Gromov-Hausdorff distance between pi1 with this ultrametric of the two spaces is less than or equal to twice of the Gromov-Hausdorff distance between the original spaces. And then continue with some more examples on the dendrogram and some more interesting examples. Consider the unit geodesic circle associated to p pi1. We have the following dendrogram structure. So the y-axis represents the elements in pi1. Each integer corresponds to one class in pi1, and all of the classes is born at 0 and it dies at 2 pi over 3. Sorry, did I hear people speaking? Okay, probably not. Yeah. Okay, so the dendrogram. Okay, so each bar in the dendrogram is born at 0, dies at 2 pi over 3. So at 2 pi over 3, every bar merged together and they all die together. And that's how this shape tells us. Here's a more complicated example. Consider the torus, but with the two circles that having different sizes. Say R1 can be smaller than R2. Then for the dendrogram, we are seeing that there are cluster of loops that's born at 0, but they all merge to this middle loop at 2 pi over 3 times R1. And after that, everything dies at 2 pi over 3 times R2. So that's the shape of the dendrogram for the torus. And And we can also get the dendrogram structure for the wedge sum space. If you remember the one copy of S2 with two copies of S1, you take the wedge sum of those. It's a bit hard to draw the dendrogram for the wedge sum space, so I didn't put it on the screen, but you can imagine the same very similar dendrogram structure appears there. And these two spaces, they have the same first dimensional barcode that's given by these two intervals. However, their dendrogram structures are different. One way you can think of is of the difference between their dendrogram structure is that their pi1 are already different. So there's no way for the dendrograms to be the same between these two spaces. In this sense, the dendrograms is also an interesting structure and give us more information compared to just the first dimensional barcode. Okay, I'm taking much more time than I expected, so I better speed up. So this comes back. Actually, I still want to talk about.
But no worries, Ling. No worries if you go a little.
Okay, thank you. Yeah. Yes, for this slide, I just want to recall that and connect with our beginning motivation. In the beginning, I was mentioning that persistent fundamental group seems to be able to quantify the simply connectedness. So with the dendrogram structure, we can think it more precisely. So if we think of the dendrogram of this space, we will obtain a dendrogram that looks like very much similar to the dendrogram for the torus, which we have seen in the previous slide. You can see that everything dies very quickly. So in this sense, we can see that the simply connectedness for this space, I mean, a way to quantify that. Okay, in the final part, I want to talk about persistent rational homotopy. The reason to think of persistent rational homotopy is because it's difficult to deal with the standard homotopy groups. For example, for the unit geodesic circle, we have seen how the p-pi1 looks like for this space, but how about p-pi-n for n large? Following from Adamaszek and Adams' result, we know that all dimensional spheres would appear in the Vietoris-Rips filtration of S1 for the open version, and for the closed version, every sphere will appear. Therefore, if we want to know p-pi-n for S1, we will need to know pi-n of Sm for any n and any m. But this question is still not solved yet. So at this point, we are stuck here for getting p-pi-n of S1 for any n. Then we started to think, are there something that's weaker than persistent than homotopy that we can look at? And that led us to the rational homotopy groups. In 1951, Serre computed all rational homotopy groups for the spheres. For all dimensional spheres, its rational homotopy group is in fact the same as its homology group with rational coefficients. So we don't really get something new here. But for even dimensional spheres, interesting happens that we get some extra information from the rational homotopy group compared to the rational homology. And then let's move on to see that whether this extra information can also be captured in the persistent setting. The answer is yes in the closed version. And let me explain that. First, let me formulate the notion of persistent rational homotopy. By persistent rational homotopy, the way to obtain it is to simply tensor the persistent homotopy groups with Q over Z. And you can think it as point-wisely tensor. And in order to do this tensor product, we will need to require every group that appears here to be abelian. It's not a problem when n is larger than 1 because homotopic groups with dimension larger than 1, is already abelian. But if we also want to consider the rationalization of p pi 1, in that case, we will need to require the groups to be abelian. So that's a tiny remark I want to make here. And then we compute the persistent rational homotopy for S1. This is what we obtained. For n equal to 4k minus 1, the persistent rational homotopy at this dimension is isomorphic to the standard, sorry, I forgot to write the rational coefficient. So here I mean the persistent homology with rational coefficients, direct sum with this interval module. So it's a 1-point interval, and the module here takes value q to infinitely many copies. And in summary, for dimension 4k minus 1, we are seeing some extra information from the persistent rational homotopy compared to the persistent rational homology. So this comparison is just to make sure we relax the notion, but it's not so relaxed that we don't get anything new. So this example tells us that there's still something interesting with rational homotopy and something extra with rational homotopy. For other dimensions, the rational homotopy is simply the same as the persistent rational homology. And at the end, we make sure that this notion is stable, and by constructing the following stability, and in fact, it simply follows from the stability of p pi n, because the process of doing tensor product is functorial. And again, for p pi 1, we need to be careful to require the space satisfy the condition that is p pi 1 will be a persistent abelian group. And that's a tiny remark. Yes, that finishes my talk. And here's the references I mentioned in the talk. In particular, I want to highlight our project, the paper Persistent Homotopy Groups of Metric Spaces. So the same title is available on arXiv if you're interested. And that's all. Thanks for your attention.
Thanks so much, Ling. So before we get to questions, why don't we unmute ourselves and applaud for the speaker. All right, so questions for Ling.
Could I ask a quick question?
Yes.
Go ahead, of course.
Okay, so excuse for the background. There's another Zoom with my kids. So in the dendrogram is actually what really interesting. Can you show one simple example? I think maybe the first example of your pi 1. Yeah.
Yes.
So in this particular case, if I understand correctly, okay, I guess my question is, what's the relation? We know there's a relation between dendrogram and barcode in the persistent homology situation. And now, can I make the claim, and correct me if I'm wrong, that this dendrogram is sort of like the barcode for the kind of glue of barcode of the persistent homotopy? Can I think about that way, or there's some fundamental differences here?
I see. I think it depends on what you mean by barcode. To me, barcode means you first have the decomposition, and each interval represent one copy of the decomposition. In that sense, I would say it's different because decomposition of groups are very complicated. And in fact, for persistent groups, it will get even harder. At this point, we don't yet have a decomposition theory for persistent groups. So in that sense, that's different. So I'm not sure whether I answer your question completely.
So yeah, I guess sort of the natural question is if the dendrogram still captures the evolution of the pi1 groups in this picture, right? So
Yes.
in a way that it does describe the evolution of it, but it does not necessarily admit, or at least you don't know, our sort of decomposition as in the case of persistent homology. And maybe that's okay, because maybe this is already a very powerful descriptor for the homotopy, relation between homotopy. We don't necessarily need a decomposition, but it would be nice to see some form of decomposition, whether one exists.
Yes, I see. Yeah.
Thank you.
Ling, could I ask a follow-up question about the dendrograms?
Yes.
I was curious if you think there's any hope to sort of relate this to the work. I mean, actually by Bay and I think 6 other collaborators on I think they looked at Czech persistent homology of Czech of metric graphs, and then Verk looked at related things, persistent one-dimensional homology of Rips complexes of geodesic spaces, which I think you're also looking at geodesic spaces. So I was trying to think if there's some sort of Hurewicz theorem, right, to go from dendrograms to barcodes, but maybe the settings are too different, right? Like you have in your dendrogram, you have I'll call it a bar in your dendrogram for each element, whereas in homology, we usually put a bar for each generator. Yeah, any hope for persistent or Hurewicz and this Booleanization, right? That H1 is a Booleanization of pi1, or are the contexts too different?
I actually think when you mentioned that the relation between them is that PH1 is the Booleanization of pi1. I haven't thought it deeply, but I do think that we could obtain information of PH1 from P pi1, just taking the Booleanization. Yeah.
More questions? All right, people are going to have to interrupt me because otherwise I'm going to abuse my privilege, and I've got at least 2 more questions for you, Ling, but I'll give people a chance to interrupt me in the middle. So I wanted to ask about your example near the beginning where you distinguished P pi1 from PH1 on the torus from the 2 sphere along with 2 circles attached. Yeah, this example. So I was curious, could you also get this example to work to distinguish P pi n from PHN if you take an n sphere across an n sphere versus a 2n dimensional sphere wedged to 2 n spheres? And I mean, we need to sort of know, like, when the n dimensional bar dies in the Rips complex of the sphere, but I think we know that from different perspectives now. Have you thought about this, or do you think that would work, or do you know it doesn't work? Or
yes, we do have some discussion toward this direction. If I recall correctly, I remember in the paper we mentioned that S1 cross Sn had some similar discussion in those examples as well. Yes. Mm-hmm.
To distinguish P pi n from PHN.
Yeah. Yes.
Oh, okay. Oh, perfect. Okay. Very cool. And then I wanted to ask a question. Oh, let me see if other people have questions first. Yeah, go ahead. Oh no, if you got me and Bay tag teaming, that's a bad situation to be in, but go ahead, Bay.
Oh, yeah. So I just want to ask a question because I also have a question on this particular slide. So in this particular case, you are, again, correct me if I'm wrong, you are basically saying that there are spaces that you can construct which are not distinguishable through persistent homology, but is distinguishable through the persistent homotopy groups. But I don't know if I missed this, since I missed the first few minutes of your talk, is there an obvious way to compute P pi 1? What are the necessary ingredients for its actual computation. I mean, with a sphere, I think there's really nice results that, you know, Henry and the co-authors had that you can look up to. But do you have sort of a general, what is the sort of rule of thumb to recover p-pi1?
By computation, do you mean in a computer or just theoretically?
Both theoretical or the computer, you know, like what are the ingredients that you would need?
I see. Yeah. So first of all, I guess you will get disappointed because anything involves groups, the computation in general, the computation is NP hard. And the way you think of it, the groups is you can think of you want to compute a set of generators of the group and then a set of relations between those generators, and they together forms a presentation for the group. I think from the computational aspect, that's what you would want to get in your output. But it's known that it's NP hard to compute to check whether a loop is trivial or not. In general, this is NP hard. So, but I'm not sure whether there are like very simple situations where the computation becomes more reasonable or not. Well, yeah, so that's for the computing in algorithms. Well, theoretically speaking, at this point in my examples, what I did is in fact first obtain the Vietoris-Rips homotopy types and then apply the homotopy functor on those to get some examples. Yeah.
So in a way, right now you could rely on sort of Henry's previous work, almost like a dictionary, and then sort of look up and then translate to your setting.
Yes, I would say that's a reasonable way to think of that. And I also do want to mention that in the study of discrete fundamental group, so this is how Plaut and Wilkins, they study this notion. You see that nothing about Vietoris-Rips is involved. In fact, Wilkins computed this example in the discrete level without using any like Vietoris-Rips. So they have, let me see. I don't know whether their method can be generalized, but at least in the examples involved in their paper, it's simply using the definition at this level to compute the discrete fundamental group. Yeah.
So in summary, it's not completely hopeless that there's still maybe some possibilities of going from the discrete version.
Yeah, I would say so. And to my understanding, the hope would lies on getting some invariance from the persistent groups. If computing persistent group is hopeless, then we probably want to seek for some computable invariance. Yeah. For example, this paper in the knot theory, Letscher is actually not dealing with the persistent fundamental groups directly. He obtained an invariant called the Alexander modules. So that's also those passes we can look at.
More questions for Ling?
Yeah, hello.
Yes.
Yeah, I'm much concerned with your homotopy. That's the persistent homotopy, the diagram that Henry was talking about, with the torus and the sphere, gluing the sphere and the circle together. That's the two sphere, the gluing of the sphere and the circle. I don't know, but I think how sure are you that the persistent homology, the persistent homotopy of the torus is homotopically equivalent to the persistent homotopy of the sphere, the one sphere and the two sphere all glued together? Because I'm thinking if you are to take, you said for all n, so let's say if n is equal to 2, that means for a circle, the second homotopy of a circle, you are getting 0, because if you are looking in terms of the homology, if you are taking the second dimensional whole of a circle, there's nothing there. like you take the fundamental group, let's look at the fundamental group. If you take the first fundamental group of a circle, that's the S1, you are getting your integers. But if you take the second fundamental group of your X1, you have nothing there. So if you are gluing together, I don't know if, is that going to change the homotopy of your already attached, your gluing and space, like the sphere and the two circles being glued together? And how sure are you that at the end, if you compute, they are going to be homotopically equivalent?
Sorry, I'm not sure I totally understand your question. Do you mind to summarize in maybe 1 or 2 sentences what the precise question is?
Okay, okay. You said for all n, that was the emphasis that you are making. That's for all n. That's if you are having your n being 1, 2, 3. So I'm saying it in terms of n being 2.
Okay.
When your n is 2, what happens to your one sphere for n being 2? Because the one sphere is a one-dimensional object. So when n is 2, you are moving towards two-dimensional. What happens to your one-dimensional sphere?
Ling, do you mind if I think I might understand the question. So
okay.
David, I think what the way Ling answered my question is, you know, on this slide, figure 1, she shows how these are 2 examples where they have the same pH1, but they have different p pi 1s, right?
Yeah.
Okay.
And so we were discussing, do you have analogous examples where you can find different spaces where they have the same pHn, but different p pi n's, right? So it's not that, you know, if you fix a space, pH1 is the same as pH2 is the same as pH3. No, it's more like this example showing how one invariant doesn't distinguish these 2 spaces, but another one does. You can sort of generalize that example to all dimensions. I don't know how well I did. Yeah.
Okay.
And thanks for clarifying.
I'm just concerned with you saying that for all n, maybe I think you should actually exempt, because if n is greater than 2, I don't know how you're going to compute the persistent homotopy of that surface if n is greater than 2. So I don't know, maybe if you have to reduce the n to be less than 2, so that you can get, because from the work that you've done, you just computed the persistent homotopy for just your pH1 and the pi 1, but you've not done any work on the pH2 and the pi 2. So
that's you're saying for the first bullet point, David.
Sorry, I was thinking maybe, David, are you asking that I didn't, you think I didn't like define p pi n, or was that the part of the question? It was confusing to you what p pi 2 means?
I'm looking at, since you said your n, so I'm thinking maybe your n, you can take your pH1, that's the pi 1, and your pH2, that's for the n. Let's say if you have your pi 1, that's the first fundamental group of your x1, then you move on to your second fundamental group, that's the pi 2 of x1.
Okay.
I don't know if, yeah. So if you are taking your pi 1, the first fundamental group of your x1 cross your x1, which is the torus, if you take the first fundamental group of your torus, what are you getting? What's the value for your torus? And how are you, I'm trying to see what numbers are you getting, generating to see that the torus and the glued sphere and the one sphere are homotopically equivalent for all n.
So
but that's homology. That's at the level of homology. That first bullet for all n.
Yeah.
Yeah, this one. Yeah.
Yeah, so this is saying at the homology level, they are isomorphic. And the way that this formula comes from is in fact because of the results from these 2 papers, the Vietoris-Rips restricted to that interval of the two spaces are homotopy equivalent. Therefore, their persistent homologies. No. What I'm saying, not they are homotopy equivalent to themselves. They are homotopy equivalent to their base space. So let me write.
I see you're restricting the scale parameters that you're looking at here between 0 and 2
Yes.
zeta.
Yeah, you just look at this, then for any t, your Vietoris-Rips of the corresponding spaces is the same as your base space. So the question of computing them is the same as computing them in the static case.
Oh, okay.
And because the two space themselves has the same Hn in all dimensions, it somehow follows from there that when you apply Hn on the left-hand side, you also obtain the same result. Does that answer your question?
Okay, so it's based on the assumption from the two works being done by Adams and Ling that you conclude that since they all have the same Hn, then if their rips are the same, then probably if you are putting the Hn on them, they are also going to be the same.
Yeah,
right?
because all of the
Okay.
isomorphics, they are natural, so we can pass to the persistent setting. Yeah.
Oh, okay. Okay.
Yes.
I think I get it now.
Okay. Yeah, that's great.
So I hope people feel free to leave. Ling, is it okay if I ask one more question?
Yeah, sure.
I wanted to clarify the rational homotopy of rational persistent homotopy of the circle example.
Okay.
So first, the result by Serre is sort of saying that if you go back, so for an odd sphere, the rational homotopy is the same as the rational homology.
Yeah.
Oh, what's the difference between the first displayed equation and the second displayed equation?
The second one has
for the even sphere.
Extra value.
Okay, so the second one is for the even sphere.
Oh yeah, it's for the even sphere.
Okay. So then if you go to the consequences for the circle.
Yeah.
So okay, so you're looking at dimension 4k minus 1. So you're looking at odd dimensional. And so
yes.
I mean, on the right hand side you have a direct sum, right? Like, where are these two terms coming from? Like, are they both coming from the regime where the Rips complex of the circle is an odd sphere, or are they coming from the regime where the Rips complex of the circle is an even sphere? Or yeah,
it comes from the even sphere and comes from dimension 4k minus 1.
And then that's still persistent over this range of scales?
Yes.
Okay. How does because like the even dimensional spheres that come up in the Rips complex of the circle, they're not persistent. So what's the intuition for how they give this persistent effect in the rational homotopy?
What do you mean by they are not persistent?
Like they only exist for a single scale.
Oh, this difference also, they only appear in that single scale.
Oh, I see. That's a single scale, not a range of scales.
Yeah, it's just one point.
Okay.
A cheating notation, sorry.
No. I'm totally with you. Okay. Cool. Well, let's end the recorded portion there. Maybe we can have more time for discussion in the non-recorded portion. But thanks again, Ling, for a fantastic talk, and thanks everybody for the nice questions.
Thank you.